All right. Well, thank you very much, everybody. I was really, really looking forward to being here in person with you. Unfortunately, I brought a little bit of a gift back from Belgium, and let's put it this way: my wife appreciated this a lot less than the chocolates. Um, but in any case, the always a real privilege to be able to talk with people about probably the topic that I'm most passionate about, which is quantum simulation. So what the aim of this talk is going to be is it's just going to be entirely a whiteboard talk. The reason why is I want it to be interactive. I find that giving this type of a talk with a set of fixed slides, it's really easy for me to just show you all of the equations, but sometimes it's a lot harder to get the intuition behind all of this. So what I want to do is I want to take you through the basics in order to be able to get you up to the point where you can actually be a practitioner in the field of quantum simulation. And in particular, what I aim to do is I aim to teach you how Trotter-Suzuki simulations end up working, and also how more advanced ideas such as qubitization and linear combinations of unitaries can be used in order to solve problems in quantum simulation and beyond. And so many of these tools I found are useful in general for algorithm development because, well, looking at quantum simulation, you might just think, oh, this is going to be a talk about chemistry. It's actually subtly not. Quantum simulation is actually giving you a new way of solving a different class of compilation problems. So I'll present it that way, and then we'll go into some of the more practical stuff later. Also, the other thing is that my main aim is to make sure that all of you walk away with something from this. And so to that end, I think it's more important that you stop and interrupt me as soon as you have any questions about anything, because I always find that if I can learn one thing from every lecture that I've been to, I'm doing really well. So, please help me get that one thing into your brain by stopping me at any time. So taking a step back, right? Why quantum simulation? What's the origin of this? Now, the origin of quantum simulation originally was kind of articulated by Feynman. And so, this is Feynman over here, and you can tell it's Feynman because there's a pair of bongo drums over there. Clearly, my art was my best subject in high school. But in any case, the Feynman ended up noticing something very strange about quantum mechanics, and that strange thing is that if you consider the state space that you end up getting for, say, two spins that are interacting with each other, this is, a state psi, which is in a two-dimensional Hilbert space. This might be a state phi, which is in also a two-dimensional Hilbert space. But when you combine the two, the composite quantum state is in the Hilbert space that is two squared dimensions. And in general, if we ended up getting a state of n spins interacting here, then the vector that we're looking at is in C2 to the n. And this ends up saying something really strange and interesting. What it ends up saying is that small numbers of interacting quantum systems live in a state space that is absolutely enormous. So to give you an idea, right? Let's say we wanted to simulate a cup of water. The cup of water is, roughly speaking, going to contain 10 to the 23rd atoms, which is probably on the order of like 10 to the 24 electrons. Okay, so now if we just look at the spin degree of freedom for this, the size of the vector that we would need to describe just this one tiny itsy-bitsy little piece of the universe would be a Hilbert space of dimension 2 to the 10 to the 24. And that is absolutely an astounding amount of memory that would be needed in order to store the state vector. And okay, so why is that weird? or interesting? Well, from a philosophical perspective, the way that I like thinking about this, and is that if we consider the world, which probably looks something like this. Oh, I guess there's this like Europe part over here and stuff. But in any case, all of this really, if we like to think about it, I like to think of the entire universe as a computational system that has a number of inputs and a number of outputs, i.e., the universe simulates itself. Now, if we think about the universe as a gigantic simulation, the question is, what would be the computational power needed in order to be able to simulate the universe? Now, what this suggests is that if the universe is fundamentally solving the Schrodinger equation for all things, then it would have to be a Turing machine of absolutely absurd power to be able to simulate the Schrodinger equation as we conventionally write it for those atoms. And this is fascinating because it begs the question, where does the universe hide its computational power, and what characterizes the computational power of the universe? This approach over here really ends up, or this argument over here, really forms the foundation of what we end up calling the quantum Church-Turing thesis, which is the belief that the universe, or all reasonable models of computing more broadly, really shouldn't be thought of as a giant Turing machine that is storing vectors of this absurd dimension, but instead actually is a quantum computer processing quantum information. And so what simulation then is about is it gives us a way of addressing this question. If we end up having a molecule over here that is evolving according to the rules of quantum mechanics, this allows us to ask the question, well, what is the cost of simulating quantum mechanics for even just an atom? And for systems even of a small number of atoms, it can be incredibly daunting. And one of the aims of quantum simulation is really to be able to place bounds, upper and lower bounds, on what the cost of any quantum computer doing such a simulation would be. And also, to be able to ask, well, are there practical applications? Can we do interesting things in the case of chemistry or other areas? And one of the benchmark problems that my collaborators and I came up with is this problem of FOMOCO. Okay, just to give you an idea about what practical things could be done with this. Now, FOMOCO is something that's really interesting. What it is the active site of for a particular reaction that ends up being catalyzed using this enzyme called nitrogenase. And the reaction that's being catalyzed by this is essentially biological nitrogen fixation. And so what we do over there is we have something like what? We've got N2, I guess, I'll put an X and Y here because I don't trust my brain to get the right stoichiometric ratios. But what we want to do is we want to convert this over to ammonia in the end. And the standard way that this is done industrially is using the Haber process. The Haber process, invented by Fritz Haber, is one of the most important chemical processes that's been developed to date. It single-handedly actually kept Germany in the First World War by giving an artificial way in order to be able to make munitions, when previously people would have to actually, mine many of the nitrates that were needed for it. This process allowed them to make it literally from natural gas and nitrogen in the air. And also, it's responsible for about 1% of global energy usage. So basically, almost all the fertilizer that we use in order to maintain our crops is produced by the Haber process. And to give you an idea of also its importance for fertilizer, If some of you might have heard the term the dismal science used to refer to economics. This came about because of an economist by the name of Malthus, who predicted that at the end of the 19th century, we'd run out of food production. And actually, he wasn't wrong. But the thing that Malthus didn't consider is technological innovation, like the Haber process, which gave us a way of making scalably fertilizer at the price, though, of an increasingly large amount of energy being used, just to end up making the ammonia that we need to feed the world. So this is a major thing. And the reason why this process ends up happening is because of the fact that nitrogen, if you think about it, is this diatomic molecule that has an incredibly strong triple bond between it. And in order to be able to break it up and push this over to NH4, we've got to figure out a way of slicing that triple bond down the middle. Now, the way engineers do it is the way engineers do many things, through brute frickin' force. So what they do is they put this under intense pressure, something like around 900 atmosphere, and very, very high temperatures in order to be able to provide enough energy to slice that bond. And this is the reason why it ends up using about 1% of global energy, because of these resources needed in order to be able to make ammonia. Okay, cool, fantastic. I've just wasted your lives talking about ammonia. Why is this relevant? Well, the reason why it's relevant is because of this molecule, FOMOCO, which sits at the center of this nitrogenase enzyme. Because bacteria have actually figured out a way of building a catalyst that acts essentially as a molecular knife to split that triple bond down the middle. And that's what FOMOCO ends up doing. It allows the bacteria to be able to produce ammonia at room temperature and pressure. So the only problem with it is that this process ends up is incredibly sensitive to oxygen. So it doesn't actually end up working at an industrial scale. It only works well inside a cell membrane. And unfortunately, also, we don't actually understand why it works. The reason why we don't understand why it works is because of the fact that it ends up forming this iron molybdenum complex in the middle. And what happens when you end up having incredibly heavy atoms inside of molecules, you tend to have this effect known as strong correlation. This ends up happening because the electrons, which you can envision circling the atoms, they end up getting sucked in to tighter and tighter orbits as the charges end up increasing. And that causes the electrons to now become much more strongly interacting with each other because they're all compressed physically into a smaller space. And the amount of entanglement that we need in order to be able to describe this system ends up becoming quite large. In fact, too large for known classical methods to do a good job of modeling these systems. And so in order for us to be able to solve this problem, we really kind of accurately, at least, we need quantum effects to be treated very accurately. And so this is one of the best applications that's been found to date for quantum computing. And the idea basically behind how we would use quantum simulation to solve this problem is we essentially end up taking a molecular model of this system, and we map it into a set of qubits inside our quantum computer. And then we simulate the dynamics of this. So in some sense, what we're doing is we're tricking our quantum computer into thinking that it's that molecule. And then by measuring the qubits in an appropriate way, and I'll show you how to do that soon, we can actually extract all the relevant information that we would get from performing an experiment just by measuring the qubits in our quantum computer that are logically equivalent to the electrons in the system that we're simulating. So in that sense, we're kind of building the molecule inside our quantum computer. and probing it in order to understand it. And the dream would be that by simulating the molecule like this on a quantum computer, we might be able to understand the mechanism by which this iron molybdenum complex ends up severing the triple bond for nitrogen to lead to cheap ammonia production. And to give you an idea about the cost of this, and this is about the currently the record for quantum simulation here. We need about on the order of 1 billion quantum gate operations to be able to carry this out. And with quantum error correction, this corresponds to about on the order of 200 logical qubits. And it with slightly better error rates, translating this through the surface code, this is about on the order of 1 million physical qubits. So to put this in perspective, where are we right now? With quantum computers, physically, we've made huge strides in the last couple of years. We've gotten to the point where devices like the IBM quantum experience has 127 physical qubits. And with the gate error rates that we've got at the moment, we can do circuits that are, have depth less than or equal to about 100 gates. So the moral of the story is that we're a long way off from where we need to be for this. And this is one of the reasons why quantum simulation is so important now to look at, because these are compelling applications that we can do that are much more relevant for many people's lives than something like violating people's privacy using Shor's algorithm. This really could change the world, but there's a huge gulf between where we are right now on the order of about 100 gates and the billion gates that we need to do it. And the development of increasingly advanced simulation methods, as well as better forms of quantum error correction, will be needed in order for us to bridge this gap. And so my aim is to be able to teach you, the general art of this process. And that basically what that art is the art of translating a physical system into a sequence of instructions that tricks the quantum computer into thinking that it's that physical system. Okay, but before I begin, does anybody have any questions? Cool. Okay. Well, please interrupt me later, because I know for a fact I wasn't crystal clear there. So let's begin with the abstract notion of quantum simulation. So let's define what the problem is. Okay. So in general, what we have is quantum simulation is often taken to be synonymous with the term Hamiltonian simulation. So let's assume we have a Hamiltonian. And there's many ways I can state this. A Hamiltonian is basically a Hermitian matrix, meaning that the matrix H is equal to its own conjugate transpose. And let's assume that the Hamiltonian can be written in the following form: sum over I, A, I, U, I, for an appropriate set of unitary operations. Our task is to implement e to the minus I, H, T. We want to approximate this with a product of gates Gj such that the operator norm of e to the minus IHT minus pi GJG is less than or equal to epsilon using a minimal number of gates. Okay, and here in general, H we would like to think of as being a complex 2 to the n by 2 to the n. Two. Blame that on the COVID. A complex 2 to the n by 2 to the n matrix. So basically, high level, that's the statement of the problem. And let me just motivate this particular form over here. Where does this come from? Well, for those of you who've done a lot of physics, it's second nature, but not everybody comes to quantum computing from a physics background. So if you're coming from it from more of a computer science background, this ends up coming about because this is the solution to the fundamental differential equation of quantum mechanics, which is known as the Schrodinger equation. Okay, the Schrodinger equation ends up taking the following form. It gives you the time evolution of a quantum state via the solution to the following equation. D psi of t by dt is equal to negative I h psi of t. Here, I've assumed for simplicity that h is time independent. So there's no functional dependence on this matrix H. It gets just a little bit more complicated, but nothing conceptually changes when we do this. This H over here, again, is what we call the Hamiltonian. And physically, the Hamiltonian can be interpreted as the energy operator. And it has the property that for any state, psi, the sandwich of psi with h in the middle, this is equal to the average energy for the system. So how does this work in general? If you want to simulate a particular Hamiltonian, like a physical one, like chemistry, for example, what you would do is you would talk to a chemist or you talk to a physicist. They'll give you a specific representation of that Hamiltonian that conforms to this form up here. And then your job is to solve this particular problem in here. So from that perspective, actually, the problem of simulation is a compilation problem. Now, normally, compilation problems you think of in the following way, right? Let's say that what I wanted to do is, I wanted to, I've got a unitary matrix. Let's say cosine theta, sine theta, minus sine theta, cosine theta. And I'd like to be able to convert this over here to individual gates. Well, in this case, it's pretty easy. It's just actually an RY rotation. But in general, the problem usually for compilation is the following. You know the matrix U, where this is U, and you want to find a gate sequence product over J, GJ, such that the difference between that is less than or equal to epsilon for some epsilon greater than 0 that you'd like to pick. Okay, so this is a normal compilation problem that we have to solve all the time when we're trying to translate a unitary matrix that we want to build into a sequence of discrete gates that our quantum computer actually has. So the key thing is that we know what U is. Now, let's take a look at the Hamiltonian simulation. The solution to the Hamiltonian simulation problem over here, it can actually be rewritten in a different way. If we define psi of t to be equal to some unitary matrix, U of t, this thing is known as the time evolution operator. Then, by plugging this into the Schrodinger equation, we end up getting the following differential equation. D by dt of U of t is equal to negative I h U of t. And the solution to this is just U of t equals e to the minus I h t. So what this ends up saying is that if we want to find a time-evolved state at time t, all we need to do is put in an initial psi of 0 and apply e to the minus iht to it. And then we'll end up getting the final state. The problem with the simulation problem is that we know h and t, but not e to the minus iht. And what we want is to find the a sequence of gates, gj, such that the norm of e to the minus iht minus the product over those gates is less than or equal to epsilon. So it's very similar to the general compilation problem. The difference is what we know. We know the exponent of the unitary. We know this h and t, but we don't know the form of the matrix itself. In the standard compilation problem, we know u, but we don't know this. And so why is this fair? Like, why can't we just figure this out? Well, let's take a look at what e to the minus iht is. We can write this as the sum from j equals 0 to infinity of negative I ht to the j over j factorial. So if we wanted to figure out the matrix elements of this, this operator, what we'd have to do is we'd have to, at second order, we'd have to compute, let me actually just do this to at least second order. This is minus I ht minus h squared t squared over 2 factorial, so on and so forth. To find this term, what we have to do is we have to multiply 2 to the n by 2 to the n matrices. And so explicitly coming up with an expression, even if we know what h is, for what u is extremely difficult. In fact, this problem is so difficult that in general, we don't believe quantum computers can actually figure out all these matrix elements precisely. So it's kind of a weird version of a compilation problem because we know the generator of the unitary that we want to build, but we don't know the unitary. And the art really behind all of this is to come up with tactics that are going to allow us to compile this evolution over here into a sequence of gates without needing to know that information. And surprisingly, you can do it. Now, any questions here?
Are these approaches limited to, just the Schrodinger equation, or can we map this onto other physical simulation things like Lindblad or Kohn-Sham stuff?
Okay, so Lindblad, no. The stuff that I'm going to be teaching you today, not directly. The big problem is that, if you're taking a look at the dynamics that you end up getting from a master equation, it's non-unitary. And so you have to, because quantum computers only natively know how to do unitary dynamics, you're not going to be able to come up with this direct mapping between the channel that you would end up getting in an open quantum system and the unitaries that you can actually pull off on the quantum computer. So instead, what you need to do is you need to embed that, that channel as a unitary in a higher dimensional space and then go through that compilation. Specifically, the technique, and I'm going to mention it, a linear combination of unitaries can be used to pull it off, but simulations of master equations are much more subtle than the closed quantum system simulation that I'm going to be talking about, and still is an active area of research. So you can tackle it, but it's much more complicated, and the formalism that I'm primarily focusing on doesn't really address it. Does that make sense?
Thank you.
Can you comment on analog quantum simulation in this context?
Oh gosh, yeah. Okay, so I've got a reputation when it comes to analog simulation. All right. So unfortunately, you forced me to pull to talk about my controversial views on analog simulation. So my view on analog simulation is, unfortunately, the idea behind analog simulation is really simple in some way. Let's say that what I wanted to do is I wanted to simulate I wanted to simulate H2. Okay, so we've got two protons over here, and we've got some electrons. Let's say we're talking about like a sigma bond that we want to do, which, if I recall right, looks kind of like that. So in any case, the idea behind it would be you've got these two electrons that are floating around inside this blob here. Rather than thinking about a sequence of gate operations, the idea would be, well, let's come up with, say, a trap in an appropriate way that would put electrons in, say, two different wells of this. And what we would like to be able to do is we would like to be able to take, unfortunately, H is used in three different ways here. It's used for hydrogen, it's used for Hadamard, and it's used for Hamiltonian. I apologize wholeheartedly for this. But in any case, we've got, I'll call this H hydrogen over here. The idea basically behind an analog simulator is to tune your experiment in such a way so that the analog simulator, its Hamiltonian is going to be approximately equivalent to the hydrogen atom hydrogen atom Hamiltonian. And then effectively what you're going to have is these electrons at that point, up to a change of basis, then are literally going to be bonded in exactly the same way that you would end up having in a molecule. So for an analog system, really is just a tunable quantum system that is capable of having in principle, the same dynamics that you end up getting for the original system. This is actually very popular right now because of the fact that you don't need the same level of control that we've got for this for quantum computers, and on top of that, you can end up as a result scaling us to much larger systems. Rydberg atom simulations of 1,000 plus qubits are possible with analog. Whereas if we're looking at digital, we really struggle doing simulations beyond about 12 qubits. So this sounds like analog comes up like gangbusters, right? Because of the fact that it's much more. Right now, we can handle huge simulations, but unfortunately, I don't think that, from my perspective, the way that we're approaching analog simulation at the moment really actually is solving the same computational problem that we try to solve with a digital simulation. The reason why is that our goal for simulation is this over here. We want to perform a sequence of operations on our quantum computer such that the error is promised to be at most epsilon. So this is something that's really cool because we guarantee that if you execute this algorithm with accurate enough gates, then we can guarantee you what the error will be in the worst case scenario, i.e. you can trust the results that end up coming out. And this is predicated on the fact that you can characterize and error correct individual gates in a discrete model, but you can't do that with an analog model. In this case, what you need to do is you would need to do an incredibly accurate characterization of the system in order to be able to guarantee that this relationship that you posit is true actually is close enough in order to guarantee that you're within epsilon error. And nobody knows how to do that in a scalable fashion. So because of this characterization problem and the challenges on control, like to give you an idea, to solve the FOMOCO problem with an analog simulator, what you would need to have is the amount of stability that you would need is you would need to ensure that the parameters that end up describing your system, they would have to drift at a rate of 1 radian per billion years of continuous evolution. And the IBM quantum experience or most other things, arguably ion traps might be able to hit this. But by almost every quantum technology will have a far faster rate of change of the physical system than the amount that would be needed in order to be able to do a simulation like this within the error needed to make it relevant. So this is the big problem, and why while analog simulation is neat, it isn't clear what we would need to do in order to be able to allow it to solve the computational problem that we care about. Does that answer the question?
Yeah, I had a question about the fact that like when you stated the Fomoko problem, you assumed that like the Hamiltonian given to you is like 100% the real system, like there's error there, right? So how does that error compare with like the inherent limitation of the analog error? Because if the initial Hamiltonian was sort of close enough but not really the thing, then maybe we can do close enough but not really the thing on the second step as well.
Right. Well, the difference is that the difference is that with the analog quantum simulation, there's no way of systematically throwing more resources at it in order to be able to make it more accurate. If you've done if you take a look at the calibration process, there's always going to be errors and there's always going to be noise, and there isn't a clear algorithm that you can carry out in order to be able to reduce that error down to zero. With the threshold theorem for quantum error correction, that you can reduce down to zero, and we can solve that computational problem within error epsilon for any epsilon greater than zero. And so that's one of the biggest advantages. Yes, there's always going to be this issue about whether or not the Hamiltonian that you're programming in is the physical Hamiltonian that you care about. But our problem isn't even about the physical Hamiltonian. That's a problem for the physicists and the chemists. Our problem is, given a mathematical model of a Hamiltonian, can we simulate the dynamics of that mathematical model? Then it's up to, of course, the user to decide whether or not their particular Hamiltonian is good enough for their purposes.
For this framework, have people tried looking at like probably approximately correct, so not guaranteeing epsilon, but guaranteeing epsilon with a certain probability? And does that help the bounds a lot in this case, or?
Yeah, actually, technically, it helps. It helps a little bit for some algorithms. For some of them, actually, it will be true uniformly, but depending on some algorithms that have an element of randomness to it, those forms, what we'll demand that it be less than epsilon with probability greater than 2/3, say. And then what will happen in those cases is it ends up causing differences by logarithmic factors. Because what you can do is you can always use statistical amplification via majority votes in order to be able to take the erroneous simulations and vote them out just by taking the median of a bunch of other simulations. Anything else? Okay. Cool, but now that I'm back here, there's one other thing that I wanted to address. I assumed that my Hamiltonian is a sum of unitary matrices. Okay, that's something that's going to be useful here for these methods. But for any finite dimensional matrix, actually, without loss of generality, it's always a sum of unitary matrices. Does anybody see why that's true? I see a hand in the back, maybe.
Is it because like the unitary matrices are closed under addition?
Actually, they're not. They're not. Yeah. Here, let me give you an example. This example is really cool. All right. So let's consider identity plus poly z over 2. See, I've spent too long in Canada. It's poly z for me now rather than poly z. They've been those Canadians are just warping my mind. But in any case, this matrix over here, when we add them together, is just 1, 1 plus 1 minus 1 divided by 2, right? Sum of two unitaries. And this actually is just the projector onto 0. So you can see very clearly, right? The projector onto 0 is a non-unitary matrix. So unitary matrices are not, in fact, closed under addition. They're closed under multiplication, but they're not closed under addition.
And for a qubit, we have the poly basis. So you could just tensor that together.
That's exactly correct. So because of the fact that we assume that our vector space is dimension 2 to the n, then we can actually use the fact that the poly operators form an orthonormal basis for any matrix. And so in particular, what we can do is we can define the inner product between two poly operators, pi and pj, where pi is equal to, let's say, identity tensor z, identity tensor x, so on and so forth, going all the way down to, I don't know, y tensor n. So what I mean here is these are the n qubit poly operators. Okay, and so now the inner product between two poly operators, pi and pj, is actually defined to be 1 over 2 to the n trace of pi pj. And it turns out that this is actually equal to delta ij. So poly operators with respect to this inner product end up actually forming a orthonormal basis, just like they would for ordinary vectors. So you can think of poly operators actually more generally, just a cute way that you can represent any matrix. And it's super neat that they also have physical meaning, but they're a beautiful operator basis. And furthermore, all of these guys are unitary. So if we have a generic matrix H, right, what we can do is we can end up saying H is going to be equal to the sum over I, AI, PI, where AI is equal to the inner product between PI and H, which is equal to the 1 over 2 to the n trace of PIH. So this gives you a cookbook that you can use in order to be able to take any Hermitian matrix you feel like and express it as a sum of unitary matrices. And by the way, the delta ij over here, just to give you some intuition for why it's delta ij, if we take a look at poly operators, right? Poly operators are closed under multiplication. So the single qubit bit poly group ends up to plus minus i's, consisting of x, y, and z. Now, if we look at each of these guys, z is of the form 1 minus 1. Y is of the form 0, 0 minus I. This is of the form 0, 0, 1, 1. You'll notice that the trace of this, and this are all 0. In fact, the only matrix that has a non-zero trace is the identity, which the trace of it is equal to, in general, 2 to the n. And that's why we have the 1 over 2 to the n factor out in front. So if we have two n-qubit poly operators and we multiply them by each other, if they're equal, then we'll get identity. If they're not equal, we'll get another element of the poly group. And a trace of any non-identity element of the poly group is always 0. And that's why this orthonormality property ends up holding. So it's really kind of beautiful that we end up getting this. And poly operators end up forming the exact same sort of role that we had before. They're also really nice because they're both Hermitian and unitary. And we're going to use that Hermitian property in just a second. to be able to talk about Hamiltonian simulation. So this is why, without loss of generality, we can always think of any matrix, even non-Hermitian matrices, or I should say any square matrix, as a sum of unitary matrices. Okay, awesome. So any questions before we proceed on to Hamiltonian simulation? All right, cool. So let me start Hamiltonian simulation with the way that I find people respond to the most. Let's start by building some examples. And by the time we get through these examples, you'll actually understand everything you need to in order to simulate all of chemistry. And because it's actually really not super duper hard, believe it or not. Like even I could do it. So the moral of the story is, if we're thinking about simulation as compilation, then we need to ask a question about what our gate set is. Now, ideally, our gate set should be discrete. It should be something like, Hadamard, a T, and C naught. Or if you really like my favorite gate set, it would be Hadamard and Toffoli. I love that gate set, but we're not going to go down that route. Just to make our lives easier, we're going to deal with the following overcomplete base gate set. I'm going to assume, for the sake of simplicity, we have Hadamard, we have X, Y, Z, we have C naught, and we have RZ of theta for all theta. This last bit over here is the first thing that's kind of a little unrealistic in our gate set, because obviously any gate set that contains an infinite number of elements is unphysical, because you'd need an infinite number of bits of precision to specify each of those individual rotations in there. But for simplicity, we're just going to assume that we can do every RZ perfectly. Okay? So that is, let's assume we actually got an S gate in here too. So that is basically all we need. And so our task is to be able to find e to the minus IHT and translate that into a sequence of gate operations for this. So we want to be able to turn this into a sequence of, something like, H, C naught, RZ, C naught, H, some circuit that looks like this maybe. Okay? So that's our compilation problem that we want to deal with. And I'm going to deal with this one step at a time with the easiest possible simulation. So let's assume that we've got the easiest case. Okay, actually, should I cover the easiest case or the second easiest case? Any takers? Easiest or second easiest? Okay, fantastic. You asked for it. Sadly, I'm a little bit too much of a mathematician for my own good sometimes. The easiest case is H equals 0. So if H equals 0, then we have e to the minus I H t, which is the operator we want to get. This is equal to e to the negative I 0 t, which by Taylor's theorem is actually just identity. Awesome. Okay, so the easiest case is literally this circuit. Okay, fantastic. You've done the easiest possible quantum simulation. Let's go on to the second easiest case. All right, the second easiest Hamiltonian that we could do is a single qubit Hamiltonian of the form H equals alpha poly Z. Okay, and what we would like to be able to do is we would like to be able to build e to the minus I alpha Z t equal to our unitary U of t. Anybody see how we would do this? using the gate set that we've got above. Yeah, exactly. It's just a native RZ gate. So in this particular case, the circuit for our Hamiltonian, and by the way, this would be an appropriate Hamiltonian for a spin processing in a magnetic field, for example, and a bunch of other things too. In this particular case, the quantum circuit would just be the following. It would be RZ of Q alpha T. Okay, some of you might be like, whoa, 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 whoa. What's going on with that too? Unfortunately, because of the definition of the way RZ was defined based on the Bloch sphere, it turns out that RZ of theta is defined to be e to the minus I z theta divided by 2. And this is a sad but important definition. So there'll always be these annoying factors of 2 that come around because we use this Bloch sphere-centric definition for RZ rather than the sensible thing we could have done, which is just define it in terms of z times theta, not z times theta over 2. But alas, I got outvoted when it came to this. So now we're stuck with these factors of 2. All right, everybody cool with this? So basically, you guys have already done the Hamiltonian simulation. Let's go on to the third easiest case. Third easiest case would be alpha poly X. Anybody have an idea how we could do this? I'm sorry, what was that? Yeah, so basically, again, perhaps I'm too much of a mathematician for my own good yet again, but what we're frequently going to do is we're going to keep on reducing our Hamiltonian simulations to problems that we've already solved. So in this case, we have h equals alpha x. We can use the property that Hadamard x Hadamard equals z. And this implies, of course, that because h squared is equal to identity, that x is equal to Hadamard z Hadamard. Okay, so the operator that we want to build, e to the minus I alpha xt, this is equal to e to the negative I alpha h z h t. Okay, cool. That's kind of nice. But we need another theorem in order to be able to use this. And this is an important theorem that if you haven't seen, it very well may change your life. This theorem is the following. Let U be unitary. Then U e to the a U dagger is equal to e to the u dagger for all bounded matrix A of the same dimension. Okay, so why is that true? Okay, well, whenever you're proving these things and the going gets tough, the tough use Taylor's theorem. All right, if you learn nothing more from this this talk, learn that Taylor's theorem is your absolute best friend when you don't know what the heck you're doing. Oh, and I should also put a dagger here in order to make it right. So the proof behind this is really simple. If we just take the Taylor series expansion of e to the u dagger t, this is equal to sum from j equals 0 to infinity of u dagger t to the j over j factorial. Now, let's just take a look at what happens with u dagger squared. Well, this is equal to u dagger u dagger. But because u is unitary, by assumption here, those two guys eat each other. And this is the same thing as u squared, u dagger. And in general, doing the exact same thing by induction, we can end up seeing that u dagger to the n is equal to a to the n u dagger. So that using that property, we end up getting then that this is sum from j equals 0 to infinity of u a to the j t to the j over j factorial u dagger, which just by resumming everything is just u e to the a t u dagger. Okay, cool. So that shows that what we can do is by unitarily conjugating an operator exponential, we can take the unitaries into the exponent or vice versa. This ends up saying that this is equal to h e to the minus I alpha zt h, and therefore the entire circuit can just be written as h r z of 2 alpha t h. Okay, wonderful. So what would I do for h equals alpha y? So if I wanted to do the same thing, right, but now instead of simulating x, I simulate y, what would be my strategy? Yeah. So strategy is, and I'm going to be, I'll begin by diagonalizing h, then simulate using an RZ gate. That's actually it. And so in particular, the circuit doing this, I believe, is of the form H S R, no, actually it has to be the other way around. S H R Z of 2 alpha T H S dagger. I believe that's it, but I might have had the order of the S and S daggers reversed. So this is how we end up doing Y. But the central strategy is the following. What we do is we diagonalize our transformation. And then once we've diagonalized, then we compile a circuit for the diagonal form. Okay, that's just the rule that we're going to do in general. Okay? So fantastic. Now you guys actually understand everything you need to know about simulating. Well, you almost know everything you need to know about simulating 1 qubit simulations. So because this is getting too easy, let's go on to the next case. Let's say that we now have a 2 qubit Hamiltonian. That is Z tensor Z. Anybody know how we're going to solve this?
Using control Z controller.
I'm sorry, I couldn't quite hear you there.
Using a control Z gate.
We're going, sort of. What we're going to do is we're going to, believe it or not, because we're super uncreative, we're going to follow the exact same strategy that we did here. Let's see if I can, yeah. We're going to follow this exact same strategy that we did before. We're going to take a look at what this operator ends up looking like in its eigenbasis. It turns out it's actually not going to be controlled Z, but you'll see why in a second. So, very first thing is the following. If we end up having h of this form, we want to build e to the minus I h t, right? And let psi be a state such that h psi equals lambda psi. Then it's easy to see from Taylor's theorem that e to the minus I h t acting on psi just by expanding the this out, getting the appropriate powers of lambda and regrouping is just e to the minus I lambda t psi. Okay? So what we need to ask ourselves is, what are the phases that we'll end up getting for this? So first off, the eigenbasis for this is really easy. The reason why is because Z is diagonal. So the computational basis is the eigenbasis for this. So in particular, eigenvectors can be written as 0, 1, 1, 0, 1, 1, and of course, 0, 0. These are our eigenvectors. So if we take a look at building this, this matrix, let's just apply e to the minus I ht on 0, 0. Well, the first question is, well, what's the eigenvalue for Z tensor Z acting on 0, 0? This is just equal to 1 times 1 times 0, 0, because 0 is a +1 eigenvector of poly Z. So therefore, this is just 0, 0. So this guy is actually equal to e to the minus I alpha t 0, 0. Similarly, if we do e to the minus I ht acting on 0, 1, what are we going to get?
Plus I minus 1.
Yeah, we'll get a +1 up here. E to the I alpha t 0, 1. The reason why is that the eigenvector for this is of Z tensor Z acting on 0, 1. That's equal to 1 times -1, 0, 1. And therefore, we flip the sign. So if we take a look at the overall matrix for this in the standard basis is going to be e to the minus I alpha t, e to the I alpha t, e to the I alpha t, e to the minus I alpha t. Where, just to be specific here, I'm enumerating my basis like this. Okay. So what's the pattern for where you see a negative sign in the exponent? Yeah, you'll see you'll see the negative sign when the parity of these two is even. And you'll see an odd sign when the parity is odd. Okay, that's cool. So now, fun fact, claim x rz of alpha t x is equal to rz of negative alpha t. Anybody see how this is proven? Yeah? Yeah, it's proven by your new best friend theorem, right? This is just e to the negative I alpha z t over 2 x, which is equal to e to the negative I alpha x z x t over 2, because x is unitary, and x z anti-commutes, so this is equal to minus zx, and this implies that xzx is equal to minus z. And so therefore, this is equal to e to the I alpha zt over 2, which is equal to rz of minus alpha t. Cool. So what this ends up saying is that we can flip the direction of this exponent up here just by putting a NOT gate around the outside of our target. Okay, so this is here. Let me show you the easiest way of doing this simulation. What we're going to do is we're going to have our 2 qubits over here. We'll have our state psi coming in. Now, what we need to do is we need to determine whether the parity is odd or even. So I'm going to put an extra qubit down at the bottom. This extra qubit for the astute among you won't be needed in the end. But I find that this version with the extra qubit is a little bit easier to understand. So I'm going to start with this one. So the idea basically is that what we need to do is we need to determine whether for a given input, we're in the even sector or the odd sector. And we need to do that by computing the parity. Now, the parity of two qubits can be determined by the C0 gate. Okay? So once we've done this, then this will equal, if this is state A and state B, this state down here will be 0 exclusive OR A exclusive OR B, which is just equal to the parity of A and B. So it'll be 1 if A and B are different, and it'll be 0 if they're the same. Okay? So now what we have to do in order to be able to do the rotation is that in both cases, we're putting through a phase of e to the I alpha t. So we can do it in this this fashion. We can do RZ of alpha t or actually, no, that's not quite right. We want to do the RZ down here of 2 alpha t. And then we'll flip back. Okay. And this is the simulation circuit that we end up getting for it. Now, after some simple circuit simplifications, you can see that this circuit can actually be reduced down to this. We don't need the extra ancilla qubit, but it's easier to understand because now we're storing we're storing the parity inside that qubit, and which ends up flipping the direction of the rotation. It turns out that algebraically these two are equivalent, and we can just save that extra qubit. Any questions about this setup? Okay, wonderful. So now there's how would we end up doing the following Hamiltonian? Let's do Z tensor, Z tensor, Z. Okay, anybody want to tell me what the strategy is going to be for this? Yeah, exact same strategy, exact same strategy. What we're going to do here is we're going to take a look at what the eigenvectors are. Let's take a look at 0, 0, 0. In this particular case, 0, 0, 0 is going to map to 0, 0, 0. 0, 0, 1 will map to negative 0, 0, 1. 0, 1, 0 map to negative 0, 1, 0. 0, 1, 1 maps to 0, 1, 1. You see the exact same pattern over here. We get a minus sign only if the parity is non-zero. So the way that we generalize this particular circuit is just by doing the same thing, but excepting instead of computing the parity of 2 qubits, now we're going to compute the parity of 3. So our elementary form of this simulation circuit would be to take all of these guys, put that into a 0 state at the bottom. Psi is put in for these 3. We do 3 C0s down here to compute the parity. Then we do RZ of 2 alpha t here. And then we do C0s going back out. Wonderful. Okay. And this, of course, can be simplified down to this form if you don't want the extra ancilla. Okay, great. So that's how you do it. And in general, if we wanted to do n copies, you do the exact same thing, except there's n C0s. The last example that I want to cover is let's look at the case H equals X tensor Z. How would we do this guy?
Put Hadamard's.
Using Hadamard to rotate X into Z.
Yeah, we do the exact same strategy. We diagonalize this, okay? And the way we diagonalize it is we apply Hadamards in order to diagonalize the first one and reduce it to exactly the same simulation that we had before for the 2-qubit case. Doing that gives us the following simplified circuit. Okay, where this bit in here, this bit is just the simulation of Z tensor Z. Okay, so all we've done is exactly that strategy that you mentioned. We've done the basis transformation and kind of concatenated that inside a simulation of Z tensor Z. So in these cases, actually, to be honest, all we really need to do is understand how to simulate Z tensor N. In general, everything else that we're taking a look at, we can find by reducing that Pauli operator to Z tensor N just by using a Clifford gate conjugation via this Hadamard trick that we're doing here and here. Wonderful. Okay, so that's great, but unfortunately, it doesn't quite cover everything. The biggest thing that's left on the table is this gives us the ability to do, if we go back to our Hamiltonian that we specified ages ago in our problem statement, we assumed that the Hamiltonian is a sum of different UIs over here. So we've worked out what to do for any individual UI to compile that down. But we haven't talked about what to do if we have a sum. Okay, so now, let me motivate this by another example. Okay, this one, case 7. Let's assume that what we have is we have H is equal to alpha Z tensor Z plus beta I tensor X. Shoot. This one is hard, right? The reason why is because if we tried to diagonalize this, the eigenvectors of this are the plus and minus vector, which is, of course, Hadamard acting on 0 and Hadamard acting on 1. Whereas the eigenvectors for this are of the form 0, 0, 0, 1, just the ordinary computational basis vectors. So these bases are totally different. So finding a diagonalization in general for these Hamiltonians is rough because you're going to have some knowledge of a particular structure that you can exploit in order to be able to figure out what the eigenbasis of the whole thing is. And that in general just can't be done. So we're going to need another trick in order to be able to do this. And unfortunately, it isn't enough to just do the standard simulation. So how are we going to do this? Well, the way we're going to do this is the following. We are going to use this approximation known as the Trotter-Suzuki approximation. Now, I'm not sure about whether or not you want to see the higher order versions of this, but let me just explain how the lowest order versions of the Trotter-Suzuki approximation work. So first off, let A and B be bounded operators, meaning that the matrix norm of A is less than infinity and the matrix norm of B is less than infinity. Okay, So in this particular case, the claim is that if we have e to the negative I h t minus e to the negative I a e to the negative I b t, this norm over here is in order norm of the commutator of a b t squared. Okay, so if t, basically, what am I saying here? Or imagine you had two numbers, right? I've got e to the 2, or e to the 2. E to the 2 can always be written as e times e. Okay? And that's effectively what the Trotter-Suzuki approximation is doing, except these a's and b's are matrices in these cases, or more generally bounded operators. And because they're bounded operators, their commutator isn't equal to 0. And if the commutator isn't equal to 0, then this property over here that holds wonderfully for numbers, because numbers are commutative, will not actually end up holding exactly for matrices. However, what the Trotter-Suzuki formula says is that in the limit where t becomes shorter and shorter, then actually the error in this approximation will end up going to 0. All right? And this can be proven in a number of different ways. What's the easiest way for me to prove this? Any guesses? No, because you assume that I'm more creative and I know more things than I actually do. When the going gets tough, use Taylor's theorem. So all that you need to do in order to be able to prove this is actually just to do a Taylor series expansion of the two operators. And h here, I forgot to mention, is a plus b. So what we can do is let's just take a look at the Taylor series of e to the minus I, a plus b. This is equal to identity minus I, a plus b, t minus a plus b squared t squared over 2 factorial. Now let's take a look at e to the minus I at, e to the minus I bt. This is equal to identity minus I at minus a squared t squared over 2 factorial. And then, then what we're going to have here is we're going to get identity minus I b t minus b squared t squared over 2 factorial. And then there's going to be corrections that are of order t cubed coming out. And the fact that they're corrections of order t cubed, we needed to implicitly assume that the operators are bounded in order for Taylor's remainder theorem to hold. Okay, so now this is what we have. Now in order to be able to get our result, we need to distribute these multiplications through in the bottom line. Distributing through, we get negative I, a plus b, t, and already you see that this is equal to the exact expression to first order. The second order expressions, on the other hand, end up being a little bit different. So the thing is that we end up getting from the second order expressions is we're going to get minus a squared t squared over 2 factorial minus b squared t squared over 2 factorial. And then we're going to end up getting minus a b t squared plus order t cubed. And that this term ends up coming from the cross term between the two linear terms. And the other ones ended up just coming about because of the product between the t squareds and the identity. Okay, so now we can see that the difference between the two is up here, when we square out this, we get a squared plus ab plus ba plus b squared coming out of it. And we have an additional difference between the two of AB minus BA. And so that is equal to the commutator of AB. And so that's why the error over here is upper bounded by the norm of the commutator between the two. So if you, and this is one of the things that's remarkable about the Trotter-Suzuki approximation, it doesn't matter how big these operators are. They could be enormous. If they commute, then there's absolutely no error in the Trotter-Suzuki approximation. But if they don't commute, then we end up getting error that can be shrunk by the time step. Now, the next thing that is important is the following. If we end up having we end up having e to the negative I, a plus b, t over now r, minus e to the negative I, a, t over r, e to the negative I, b, t over r, to the r. This is actually in order a norm of the commutator. Just move this off to the side. Commutator of a and b, t squared, over r. Okay, so what's that saying here? What I'm saying is that if we've got a long simulation and we break it up into r short time steps, what I'm doing is I'm saying, okay, I'm going to break up my evolution time into a series of tiny little bins over here like this. Okay, and what I'm going to do is I'm going to rapidly switch between A and B. And the analogy that I like thinking about is imagine you've got yourself one of the, like a fluorescent bulb, or actually a computer monitor for that matter. It creates an illusion that the light is on all the time when really it's actually just rapidly flicking between on and off. And that's what we're doing here. We're breaking everything up into R tiny little time segments, inside which the two terms approximately commute. And then what ends up happening is that when we combine all of the errors together, we end up seeing that in the limit of R going to infinity, as we take this finer and finer slices, the exact same sort of thing ends up happening. That the simulation acts as if both terms in the Hamiltonian, A and B, are on at the same time. Okay? So that's the idea behind it. And in order to be able to see this, we can just use our previous result in order to show that e to the negative I a t over r, e to the negative I b t over r. This is just equal to e to the negative I a plus b t over r plus some operator c, which is a norm of the commutator of a and b, times t squared over r squared. Okay, so if we end up doing this, then basically, what's the right way of thinking about this? Yeah, okay. So the right way of thinking about this is that the expansion that we end up getting for this is going to be equal to, yeah, cool. So if we have the expansion of this operator raised to the rth power, what we're going to have is we're going to have e to the negative I, or what's the right way of saying this? So let's say we raise this to the rth power, okay? The rth power of this is, there's going to be a grand total of r, choose one, different ways that we can end up having the ct squared term in. So just because of the fact that the rth power is every possible string of this, the possible strings that we can have that have precisely one error showing up in it would be something like ct squared over r squared times e to the negative I, a plus b, r minus 1 t over r. And then the next one would be e to the negative I, a plus b, t over r, ct squared over r squared, times e to the negative I, a plus b, r minus 2, t over r, and so on and so forth. You see that every single time I'm moving the position of the error to a different point in the string. And there's a grand total of r choose one of these different positions that I could end up putting this, which boils down to an order r term here. Then, because of the fact that there's r of these errors, then this ends up implying that the error, when we use the submultiplicative property of the norm, and the fact that each of these operators is unitary, and thus has a norm of 1, we end up getting that this is order r choose 1 of norm of c, t squared over r squared, which is equal to order norm of the commutator t squared over r. Okay? Just because we have r different ways that the error can show up when we end up raising it to the rth power. And the fact that the error goes like 1 over r squared means that this is actually a favorable trade-off. If we had an approximation that had error order r, 1 over r, then this wouldn't be a favorable trade-off anymore, and we get no benefit from slicing. But because of the fact that the error goes like 1 over r squared, we end up getting that this factor of r times the 1 over r squared ends up still leading to a decreasing function in r. And this shows us how we can decompose these evolution operators. And so I'll leave it there for the moment because you guys probably need a little bit of a break. But let's come back in 15 minutes and I'll show you how to put this all together. All right, so I think most of you guys are filed back now. So one question or comment that I wanted to make that somebody ended up raising is what about the following, right? What we did is we took a look at the Trotter decomposition for an asymmetric decomposition, but we could have considered it for a decomposition of the following form. We could have considered it with a symmetric composition. I/AT over 2. Now, this over here, you can actually end up seeing that this is in order norm of the commutator of A commutator B plus norm of commutator B AB T cubed. So symmetrizing this actually ends up killing off the dominant commutator term that we end up getting in the expansion. So actually, in practice, people don't use the asymmetric formula that I mentioned before. Fun fact, though, actually, it turns out that the asymmetric formula, e to the negative I AT, e to the negative I BT, this formula has error order t cubed when used inside phase estimation. So in particular, if we wanted to apply, and I know you guys saw phase estimation from Jens's lectures the other day. So if we applied phase estimation on the Trotter decomposition, e to the minus I b t, what we'll end up getting from this is we'll end up getting with high probability an estimate of the eigenvalue of the minus, or the eigenphase of this operator over here, which will be approximately the eigenvalue of a plus b times t. Okay? And then plus, you would expect actually from the earlier stuff that this would be order t squared. It turns out just for the case of phase estimation that this ends up being order t cubed. The reason why is that this error, that the commutator error that can be corrected by symmetry, can actually be shown to be higher order for the purposes of eigenvalue estimation. So most people don't know this, but actually, yeah, fun fact is that well-symmetrization is actually a really nice way to reduce the cost of our methods for dynamics. It turns out when we're using this to compute eigenvalues like we would for phase estimation, then actually, no, symmetrization doesn't help you. It's even slightly more expensive. So that is one point that I wanted to make about it. But let's go through this dumb, easy to analyze case and figure out what the cost of doing our full simulation is going to be for the case of ZZ plus IX. So just to recall, our Hamiltonian that we were looking at before is alpha Z tensor Z plus beta I tensor X. Okay, so that A then would correspond to this guy here, and B would correspond to that one guy there. And so if we take, let's assume we have R splittings. Then if we have R splittings, then our previous result says that the error is order the norm of the commutator between A and B, t squared over R. Okay, and in this case, the norm of the commutator between the two is at most the absolute values of alpha and beta. So this would be absolute value of alpha times the absolute value of beta, t squared over R. And we would like this to be equal to epsilon. And so this says that the number of time slices suffices to be on the order of alpha beta t squared divided by epsilon. Okay, so this implies that the total number of simulations that we need is 2R. And why is it 2R? Well, if we're using this formula, for every slice that we're looking at, we have to implement an e to the minus IA and an e to the minus IB. So that's why it's 2 times R, because for every slice, we need to do 2 exponentials. The total number of simulation circuits that we need is 2R. Each simulation circuit now is going to be of the form e to the minus IAT, e to the negative IBT, which in our case would can be implemented because B is identity tensor X. So this would be, using our previous work that we did, it'll be Hadamard RZ of 2 beta T, Hadamard X RZ of 2 alpha T, and then this. Okay, and we'll have to repeat this circuit that we have down here R times. So the total number of gate operations here that we end up seeing is 6. So our total number of gate operations is going to be 12R. And this is going to be in order alpha, beta, t squared over epsilon. Okay? So this tells you the scaling of the error. And now you'll note for the first time, something kind of different happening. The difference is that before there was no epsilon scaling. We were able to exactly implement absolutely everything. And here, unfortunately, we can't because of the use of the Trotter-Suzuki approximation. But we can guarantee that our simulation will be able to get arbitrarily close to the correct answer. So, if this is e to the minus IHT, what we're guaranteeing is that our simulation is inside some epsilon ball over here. And the cost of building this simulation in general is going to be alpha, beta, t squared over epsilon, where this radius over here is epsilon. So as epsilon shrinks, this cost is going to diverge, but we can make that we can make that simulation arbitrarily accurate. And this is again the thing. One of the biggest things that quantum simulation gives us is it gives us a way to have controllable and rigorous accuracy. So it allows us to say for sure that we are actually simulating this insanely complicated quantum reality. Well, okay, maybe not insanely complicated for these two terms, but in general, this would be the case. And so you can see then that this is how we would simulate the sum of two terms. If we wanted to simulate many terms, then we can do the exact same thing, right? If we had, let's say, H is equal to, A1 plus A2 plus A3, then what we can do is we could say e to the minus IHT is going to be approximately equal to e to the negative I A1 t over r, e to the negative I A2 t over r, e to the negative I A3 t over r to the r. Or if you prefer, we can think about this as just e to the negative I A1 plus A2 t over r, and then envision recursing the Trotter formula over each of those until we build up our entire product formula from this. So that's why it's sufficient to just focus our attention on the two-term case, because we can just combine the errors that we end up getting from each of them. And it turns out in the end, the errors are additive. So this shows you how to end up simulating n terms in your Hamiltonian. If we have a grand total of, if we have the fully general case, sum from j equals 1 to say some capital N over here of alpha j, pj, where these are Pauli operators. Then our cost for doing the simulation, we're going to end up seeing will be on the order of order n r, and r similarly is going to be on the order of order n squared t squared divided by r max over j aj squared. Okay. So this it ends up, sorry, I said r, I meant epsilon when we do the whole thing in the end. So this gives us a way now of taking any Pauli Hamiltonian and simulating it using these tricks that you've pulled off. And as mentioned, every Hamiltonian is every Hamiltonian can always be written as a sum of Pauli operators. However, some Hamiltonians are more natural, of course, to write as a sum of Pauli operators. To give you an example of one broad class of doing it is the problem of chemistry. In chemistry, the Hamiltonian is written in the form sum over PQ, H PQ, A dagger P A Q, plus sum over PQRS, H PQRS, A dagger P, A dagger Q, ARAS. Okay, where these operators are known as creation operators. What they'll do is they say, create an electron in site P. And AQ says delete an electron in site Q. So this thing over here, what it does is it does the following. It takes an electron at site Q and then hops it over to site P. This one over here takes 2 electrons in site R and S and gets them to scatter off of each other into sites P and Q. Okay? So that's what this is describing. It's describing electron-electron interaction via these elementary hopping operators. Now, using a technique known as a Jordan-Wigner transformation, there's actually a direct mapping between the A and A daggers and Pauli operators. And that mapping is AP dagger is equal to XP minus IYP over 2 tensor ZP minus 1 going down to Z0, because I'm being a good computer scientist and counting from 0, not 1. But in any case, that is the form of it. So everywhere, if you want to simulate chemistry, basically you just do what I told you earlier. Take those substitution rules, stick them in here, and look what circuits fly off. And basically, this is the entirety of what's done in the Whitfield-Monte paper, which is was a seminal paper on this, done in about 2010, that showed how you can simulate chemistry on quantum computers. It literally followed exactly that same template that we laid out. And so in principle, actually, as soon as you know this fact and that fact, actually everything that we did is sufficient in order to be able to understand how you can simulate quantum chemistry in polynomial time. And it turns out that the cost of doing it when you substitute everything in using these methods is order n to the 11th, where n is the number of different sites or orbitals that the electrons can be in. So this is the kind of efficiency that only a theorist can love, right? Given a choice, I don't know about you guys, but if I had to choose between an n to the 11th algorithm and an e to the n algorithm, normally I'll pick the e to the n algorithm over n to the 11th. Because at least with e to the n to the 11th term is going to be suppressed by an 11 factorial. N to the 11 is just going to take off like a bat out of hell. So this quantum algorithm is, efficient, sorta, kinda. Oh, I'm sorry, I made a mistake here. It should be n cubed. But the fact is that it just isn't that great. Now, subsequent improvements in chemistry have actually ended up bringing us down. We can rigorously end up showing simulation in general that actually is sublinear in the number of orbitals. In some cases, we can end up getting, I believe, something like n to the 2/3 scaling is the best that we can get now, with some dependence on the total number of particles coming in. But in any case, the point is that these scalings have dramatically improved from this basic idea. But already knowing this is enough for you to actually understand, in principle, how to simulate almost all of physics. And in turn, it's enough in order to be able to go back to that problem that I talked about to begin with, right? Which is, how does the universe simulate a jar full of water? Now, admittedly, water is much more complicated than than the simple Hamiltonian that I ended up writing down below. But at a fundamental level, if we just viewed this as a bunch of electrons interacting using a Schrodinger equation, we're going to get complexity that will now be polynomial in 10 to the 23, rather than exponential in 10 to the 23 by doing this. So now all of a sudden it starts becoming more plausible that the universe could be a giant quantum computer emulating these physics than it seemed when we took a look at this and thought and imagined that chemistry effectively is being run in the universe in real time on a gigantic Turing machine that's secretly simulating the world, like we're all trapped in the Matrix or something. Okay, so that's actually Trotter-Suzuki. There's almost in its entirety. The one thing that I should mention that is worth noting is that there are higher order versions of this. That in general, using high order Trotter-Suzuki, what we can end up doing is we can end up getting the scaling going from order t squared over epsilon. We can get this to go like order t to the 1 plus 1 over 2k divided by epsilon to the 1 over 2k for all k greater than or equal to 1. Okay. The problem is that it turns out there's a k-dependent factor that ends up going like 5 to the 2k, creeping along like this. And so because of this factor, you end up getting this tension between the two. When you optimize everything, what we end up getting is complexity that ends up going like t times t over epsilon to the little o1. Where this little o1 over here, what I mean this is a sub-polynomial factor. So meaning we can get scaling with time that's close to linear up to some extra factor that is smaller than any polynomial function. But it turns out actually in this case to be bigger than any polylogarithmic function. It's one of those weird, awkward sort of functions that lies between, logarithms and polynomials, but it's smaller than any polynomial. So the moral of the story is that we can get close to linear, but we can never actually beat linear scaling. Does anybody see why it would be totally implausible for us to get better than linear scaling with T for a Hamiltonian simulation?
You do better than like the actual physical system.
Yeah, that's some really good intuition there. If we're imagining a universe as a giant computer, if we could simulate the system faster than linear in T, we'd be able to simulate the universe faster than itself. Actually, we can do something even weirder than that, right? What we can do is we wanted to simulate, our jar full of water, right? We could imagine simulating the quantum mechanics of that inside a quantum computer. But the quantum computer, this is physically a quantum mechanical system too. So if we could do better than linear scaling, then why not simulate the simulation inside another quantum computer and do even better? But that's also another quantum simulation that we could simulate in better than linear time. So why not simulate the simulation of the simulation? And we could keep on repeating this until we'd be able to get our computation down to order 1 time, which is totally absurd. So that's a proof by absurdity that we can't end up getting it, which unfortunately is not a valid proof technique, although one that's frequently used in complexity theory.
Let's get Bill in here.
But in any case, the better proof is it turns out that if you could get better than linear in time, there's a reduction of the problem of parity calculation to Hamiltonian simulation. And you can end up showing that you'd be able to violate lower bounds on parity if you can end up ever doing better than scaling that goes like order t plus log 1 over epsilon. But there's a big gulf between the this subpolynomial scaling that we end up getting and the polylog scaling that's optimal. And so Trotter-Suzuki, actually to date, nobody has figured out a way of bridging this gulf fully. There's work that I did with some collaborators that partially give a way of getting around this by through extrapolation of results from multiple Trotter steps, but there's no single method that ends up existing that can actually end up achieving polylogarithmic scaling, which is a super bummer. Because we'd like to understand, if we're thinking about this theoretically, well, do we know what the ultimate Hamiltonian simulation algorithm is? Because it seems like there's a big gap between this scaling with t and the literally linear scaling that's optimal. Okay? So that's going to be the rest of the topic that I'm going to talk about. I'm going to talk about another simulation method that can get you close. I'm not going to fully justify the argument for why you can end up getting linear scaling through a modification of these ideas, but I'll at least set that up for you. So the idea, the breakthrough that came about is from this idea, LCU, which also similar ideas end up getting used in this family of algorithms known as qubitization. And so the idea of linear combination of unitaries actually goes back to that question that was asked earlier. Quantum computers are great at multiplying matrices, but can they be used to add matrices? And the answer is, yeah, actually they can be. And the idea behind doing this is that what we want to do is we want to be able to figure out a way of implementing the sum of matrices as a subblock of a larger matrix, or larger unitary matrix. So let me explain that. So I mentioned before that identity plus poly z over 2 is equal to projector onto 0. I'd like to figure out a way of building this on a quantum computer. So how would I do this? Well, my claim is the following circuit will do it. Let's assume that we have an ancilla qubit up here, that's 0, and we have a state psi down below. Let's imagine that we apply a Hadamard gate here. And now what I'm going to do is I'm going to do the following. I'm going to do a 1 controlled z down here, and I'm going to do something really stupid. I'm going to do a 0 controlled identity. Okay, the astute amongst you, or those of you who are at least reasonably caffeinated, will recognize, wait a second, 0 controlled identity? That doesn't mean a darn thing. And you're right, it doesn't mean a darn thing. It means do nothing. But I'm putting that in here because of the fact that the pattern will become a lot more clear when I talk about a more interesting case. So my claim is that if we perform this circuit and measure this over here, and get a value of 0 coming out the other side, then what we'll do is we'll map psi to the projector onto 0 times psi, which will always give us 0. In effect, what I'm claiming is that actually by measuring this top qubit, we're going to measure the bottom qubit. So let's see how we can implement this why this circuit implements the projector. And the way we're going to do it, I'm just going to trace through the quantum circuit. We have, after the Hadamard gate, we have 0 plus 1 over root 2 times psi. Now I'm going to apply the controlled z to it, which won't do anything in the 0 branch, but it will apply a z to it in the 1 branch. Okay. Now I'm going to apply the Hadamard transform, again, to the first qubit. This will give me 1/2 of 0 plus 1 psi plus 1/2 0 minus 1 psi. Z psi. Okay. Now, what we're going to do is just regroup the terms. If we regroup the terms, we find that this is 1/2 of 0 identity plus z psi plus 1/2 1 identity minus z psi. Pretty neat, right? So what this says is if I measure the 0, what I'll get is I'll get psi goes to 1/2 identity plus z psi, which again is equal to projection onto 0. But what happens if I measure 1? Well, if I measure 1, then the thing I'll end up getting is identity minus z over 2, which is equal to 0, 0, 0, 1, which is equal to the projector onto 1. So if I measure 0 at the top, then the bottom state is projected onto 0. If I measure 1 at the top, the bottom one is projected onto 1. So this actually gives you a way of doing thinking about generalized measurements. If you want to build some kind of a projector in this form, we can always do it in this particular template by using a reflection in this form. Okay, so this actually also is experimentally used really widely in some platforms, especially things like Circuit QED, where you have an ancilla qubit that you use to measure a microwave mode. And effectively, you do exactly this linear combination of unitaries trick. And the reason why I'm calling it linear combination of unitaries is because of the fact we're using a circuit to add identity plus poly z to each other, which happens in this case to correspond to a projector. So this is how we can add two things together. That's pretty freaking cool. But we can, in general, end up doing this more broadly. And let me give you this notion that is the present way that we end up thinking about this. Present way we think about this is in terms of a block matrix. So this circuit up here ends up implementing, I'll call this ULCU here. ULCU is said to block encode the operator IZ over 2 and I minus Z over 2. And, sorry, actually, I did that backwards. It should be this, question mark, I minus Z over 2. And the assumption is that the blocks are set up in such a way so that this corresponds to the ancilla qubit being in 0 to begin with. And this assumes that it ends in 0 or 1, respectively. So this gives you the block matrix form of the transformation that we're carrying out on psi. And in our case, the state that we're looking at as a block matrix can be written as this. So you see that, we're either going to do the projection onto 0 or 1 with this. And we call this a block encoding because this non-unitary operation, this projector that we want, is all being drawn inside a block of the larger unitary matrix. Okay? Any questions about this? All right, so now let's generalize this concept. It's pretty straightforward to see how we would do this to sum or difference any two arbitrary operators. If I wanted two arbitrary operators, U and V, then I would just end up changing these two operators from Z and identity to any two unitaries, U and V. And then we could end up constructing the sum or difference between them randomly. All right. Now, what we want to do next is we want to be able to generalize this. Let's assume that we have the following. I'll have a decomposition that's of the form alpha j uj. Now, I'm going to assume that I have two subroutines. I've got prepare, and what prepare does is it'll map 0 to the sum over j square root of alpha j divided through by a constant that I'll call square root alpha, where alpha is equal to sum over j alpha j. And furthermore, I'm going to assume that alpha j is greater than or equal to 0. Okay? Now, I can always assume without loss of generality that alpha j is greater than or equal to 0. Does anybody see why?
You can just push it onto the UJs.
Yeah, you just sweep it under the rug. Like if we've got a minus sign here, right, or a complex phase in general, what we can do is we can always just incorporate that into our definition of the unitary. So without loss of generality, we can take all of our alpha j's to be greater than or equal to 0. So that's the first operation. What prepare does is we've got our Hamiltonian. There's two parts of it that need to be specified: the coefficients of the terms and what the terms are. Prepare, what it does is it prepares a vector containing the coefficients of this. And naturally, that isn't quite enough in order to specify the Hamiltonian. We also need to come up with a subroutine for giving us the UJs. That subroutine is conventionally in the field called select. And what it will do is it'll map a state J psi to J UJ psi. Okay, so let's just go back to that previous example. And I want to spell out what the prepare and the select circuit are for this. In this case, we're trying to construct a 50-50 combination of identity and Z. So this is the analog of our prepare circuit. This part over here chooses whether the top qubit is 0 or 1 to apply U or V, or I or Z in this case. And this portion over here is generalized into the select circuit. So this is the generalization of the trick that we had before. And I'll just go through and prove that if the following circuit will block encode, here's my claim, prepare, select, prepare, dagger, block, encodes the sum over j, alpha j, uj operation in the 0, 0 block, i.e. it encodes it in like the top left corner of the block matrix, just like it did before. All right, cool. So let's take a look at why that's true. So the circuit prepare, select, prepare, and if I just draw it like a circuit, it would be of the form prepare, select. Actually, I guess it would be this way. Prepare, dagger. Okay. So now let's just go through that. If we begin with 0 up here and we have psi down here, and block encoding it in 0, 0 implies that if we measure this qubit at the top and we end up getting 0 piping out the other side, then what will happen is we'll have applied our sum of unitaries to our state at the bottom. So that is how this is all working. So we start with 0 psi. Now we put it through the prepare circuit. This will end up giving us a sum over j, square root alpha j, j psi, divided by the square root of alpha, just by the definition of the prepare circuit. Now what the select circuit does, if you recall, is it'll take every j and apply a u sub j to it, to the psi accordingly. So this, under select, will map to the exact same thing, except what it will do is it'll apply a uj to each of the psis, and then there's this pesky normalization condition. All right, and now, when we do prepare dagger, we are going to get a gigantic letdown, because this circuit will yield prepare dagger, sum over j, square root, alpha j, j, uj, psi divided by root alpha. Yeah, and you might be thinking, and rightly so, come on, Nathan, this is totally lame. Like, you evaluated everything up to this point. Why did you leave it as prepare dagger? Well, the problem is I can't actually evaluate this circuit beyond here. The reason why is I only defined the action and prepare on the zero state. If it acts on anything else, I really don't know what it does. So because of that, I can't come up with a uniform expression for this. But I can say that if I want the component of the state that's proportional to zero, I can express that by applying the following operator. Zero ket tensor identity. And this will end up giving me zero tensor identity, prepare dagger, sum over j, square root, alpha j, j, uj, psi. So this over here, again, is just equivalent to what I said earlier. I want success to be the case when I measure zero coming out the other side. And everything else I want to be a potential failure. So I'm just filtering out the portion of the state that is proportional to zero on the ancilla qubit, or qubits. All right. But fortunately now we know the action of prepare on zero just by definition. And that will end up giving me the sum over j prime, sum over j of root alpha j prime, the inner product between j prime and j, uj psi. Now, this, of course, is equal to delta j prime j. So this just gives me some, and there's actually also a 1 over root alpha down here, and now divided by that squared. So this will give me 1 over alpha, sum over j, alpha j, uj psi. There we go. And that demonstrates exactly what we wanted to do, right? What we wanted to do is I wanted to come up with a block encoding of this that will end up implementing sum over j, alpha j, uj. Now, one of the things you'll note is there's this factor of 1 over alpha in front of it out here. This factor of 1 over alpha is necessary because the sum over alphas that you're looking at could be large. Like sum over j, alpha j, could be greater than or equal to 10 to the 9, for example, in which case it would be impossible to represent that sum of unitary operators as a block of a larger unitary, because every unitary, right, has to have every row and column be a unit vector. And if you end up having components that are like on the order of 10 billion or 10 to the 9, then you would end up actually making it impossible to do that. So this normalization constant, alpha, that ends up coming in is what saves the day. It shrinks this vector, the vectors that you're trying to build using linear combination down to become unit vectors at the price of a reduced success probability. And the probability of success for this is just equal essentially to the square of this guy, which if I call this matrix W at the top, this will end up giving me psi W dagger W psi divided by alpha squared is my probability of success. All right. So now I've actually shown you how to do something kind of remarkable. Does anybody see what that remarkable thing is? No takers? Well, what can you do on a quantum computer normally? Like what's the point of a quantum computer at its core? I hear somebody saying something. Can you repeat, please? Yeah, it's basically a matrix multiplication thing. A quantum computer can approximate any unitary matrix multiplication. Okay. Now, does that give you a hint about what's remarkable about this circuit?
You do non-unitary things.
Yeah, any matrix, any square matrix, and by doing tricks, you can always embed a rectangular matrix inside a larger square matrix, can be written, we argued, as a sum over j, alpha j, uj, which is equal to this w thing that I described at the top. This gives you a way to promote quantum computing from an engine that was only capable using the Mike and Ike style techniques of doing unitary transformations to one that can actually do generic non-unitary transformations with some probability of success. There's a price you must pay through that, but you can actually get it to do generic linear algebra now. So this opens up a wealth of new possibilities. You can use this to simulate non-unitary dynamics if you wish, or you can use this to simulate unitary dynamics if you're willing to pay that price for the probability of success. So that is the remarkable thing about it. And now through this technique, for the first time, we've got a way of actually turning a quantum computer into a general purpose linear algebra engine. And I find that really super cool. But let's use that for our simulation problem. Okay. Now, let's say that you didn't know anything about quantum computing. One of the things you might think is okay, well, I want to simulate e to the minus I h t. Okay. What would be the dumbest way that you could possibly do this? Okay, Trotter might be the dumbest way, but apart from Trotter, what's the next dumbest way that you could think of doing this on a computer? Taylor, yeah, totally. So Taylor would be, I would like identity minus ht minus h squared t squared over 2 factorial plus. I warned you that Taylor's theorem would be a central theme in this lecture. But okay, let's imagine for simplicity, imagine that h is unitary. Then, what's this guy over here? It's a sum of unitaries. Or, in other words, it's a linear combination of unitaries. So, what can we do here? Well, all that we need to do is we need to be able to build our appropriate prepare and select circuits. So, if we wanted to do this just directly, what could we do? Well, our prepare circuit would be of the following form. Prepare would end up taking 0. Let's just take a look at our operator bases that we're looking at here. So the operators that we have would be like h squared, going all the way up to, because we got to truncate it at some finite order. Let's truncate it at hk. Okay, so that is where we're going to go. And so our select operation that we would do, that's probably the easiest one to think of here. Our select would map state j psi over here and map that to j h to the j psi. Okay, because all of our operators here are going to be either the Hamiltonian to the 0th power, Hamiltonian to the 1st power, 2nd power, 3rd power, going all the way up to the kth power. Okay, So that's what our select circuit would be for LCU. Our prepare circuit, oh, actually, I'm sorry, I lied a little bit. It will be negative I to the J out here. Because remember I said that all the alpha J's have to be positive? So we've got to smush this part over here into the definition of our operators. But, okay. So then the next part is the prepare circuit. What this will do is this will map 0 over here to 0 plus 1, plus t plus t squared over 2 factorial. I guess I need some square roots here. Plus 2 plus root t cubed over 3 factorial, 3, so on and so forth, divided through by the square root of 1 plus t squared. Wow, okay, my t's and my pluses are totally illegible. So just interpret them to be the thing that makes the most sense rather than what's actually there. It's kind of like, you know, when you're looking at a physicist's calculation that uses the speed of light, just like multiply or add enough t's until everything makes sense. But okay, so that's my prepare and my select circuit. Using the previous result, my value of alpha over here is this guy. Alpha is going to be approximately equal to e to the t. And so then this gives me a way of implementing the operator exponential. Using the previous result, the probability of success for this is equal to the psi w dagger w psi divided by alpha squared, which is equal to, in our case, psi e to the plus I h t plus order of t to the k. And then we'll have e to the negative I h t plus order t to the k. I guess divided by k factorial. I guess, no, k plus 1. K plus 1 factorial should be down here. Yeah. Okay, and then this is all multiplied by psi and divided through by e to the 2t. Okay, so now if t to the k plus 1 over k plus 1 factorial is on the order of epsilon, then this is going to be on the order of 1 over e to the 2t. Okay. And so the success probability, as you can see, falls off exponentially, which blows, right? The larger we end up taking t, the worse the probability of success is going to be for this circuit. But unfortunately, it's not fatal. And the reason why is because we can use a technique called oblivious amplitude amplification. Did you guys cover amplitude amplification by any chance? No? Oh, okay. No, not two amplitudes. Amplitude amplification. All right. So the basic idea behind amplitude amplification is the following. If you imagine you've got a state that you want, I'll call the state psi good. And this is what you want. and you've got a state psi naught. This is what you start with. What we'd like to be able to do is we'd like to be able to find a way of rotating from psi naught into psi good. And that's the idea of amplitude amplification. And it does so by using two reflections. So it builds a walk operator that I'll call, I guess, R. No, I'll call it, let's call it omega, I guess, which is defined to be identity minus 2 psi naught times identity minus 2 psi good. Okay. And to imagine what this does, it's helpful to take a look at this inside a two-dimensional space spanned by these two vectors. So let's consider this to be psi good. This is where we want to go. And we have a vector psi naught poking around out here. I'm going to assume that this angle over here is theta. Okay. So now what we do is the first thing is we do this reflection about psi good. Technically, it's about the space orthogonal to psi good. So this over here, what it will do is it'll take the component of your vector in the direction of psi good, and it'll flip it. Okay, so this is what we're going to end up getting after just applying that reflection. Now, if we reflect about psi naught, which is what we get by negative that term over here, then what we're going to do is we're going to take this vector and flip its component that is orthogonal to psi naught. So we'll get some angle up here that's of angle 2 theta. So if our state, psi naught, is equal in this parameterization to be sine of theta, psi good, plus cosine theta psi suck, then what we end up seeing is that a single application of omega will map this to sine of 3 theta psi good plus cosine of 3 theta psi suck. This is just some vector that's orthogonal to good in this two-dimensional space. So this would be, I guess, psi suck down here. Okay. So that is the, this is what amplitude amplification does. And we want to do a variant of this to boost our probability of getting the correct answer, i.e. we want to boost our probability of getting 0. So psi good over here will correspond to us getting 0. And in our context, psi naught is the ordinary state that we end up getting with zeros coming in. The thing that's interesting about this is that we only need to reflect about all the states that are flagged by all zeros coming in. And that's the oblivious nature. We don't care about part of the state for this. And there's some caveats I won't bother getting into because we're short on time as it is. But the basic idea is that if we take a look at what the probability of success is for this, the probability of success after just one iteration will end up giving being sine squared of 3 theta. Psi good. Okay, cool. So then ideally what we would like is we would really like theta would be super awesome if it were pi by 6. Does anybody see why it would be super awesome to be pi by 6? Yeah, exactly. Because then we get sine squared of pi by 2, which is equal to 1. So if this is true, if we had theta equals pi by 6, then a single operation of this will map us to 100% success probability. But it turns out angle pi by 6 is a special angle or special probability of success. this corresponds to our probability of success equals to 1/4. So this is something really kind of fun. The best, with amplitude amplification, the best probability of success you can ever have going in is 1. The next best probability of success you can get is 1/4. Weird, right? In fact, actually, if you had a probability of success of 1/2, you would want to artificially lower it to 1/4 so that way you could boost it up to 1. Bonkers, but that is exactly what you do in quantum in order to be able to raise probabilities. You lower them to one of these magic angles for amplitude amplification, and then use this trick in order to be able to boost it up to 1.
Sorry, can you repeat this? I missed this detail. So why is 1/4 good?
Okay, so if we take a look at this over here, say we want to be able to figure out theta, right? Our probability of success to begin with is equal to sine squared theta, right? And let's set that equal to 1/4. Then this corresponds to finding theta equals arc sine of 1/2. And if you look at your special tables for that, that happens to be like pi by 6. So that's why we want probability of success 1/4, because it just happens because of the special properties of, the special angles here, that this actually corresponds exactly to what probability we would want to be for one application of these reflections to boost us up to 100% success probability. All right, now let's take a look at this guy. Our probability of success here ends up actually going like the time. Now, of course, if we pick time equals 0, right, then you'd have 100% probability of success, but you wouldn't get anything done. So how are we going to pick time then? Well, we're going to pick this so that the probability of success is 1 over e to the 2t, and we'd like this to be equal to 1/4, which implies that e to the 2t equals 4, which implies that t is equal to ln 2. So if we pick t to be log 2, then our probability of success is going to be exactly equal to 1/4. And why do I want that again? Yeah, because if I choose my t such that the probability of success is 1/4, then I can use this trick to boost it to 100% chance of working. And that's the whole idea behind this approach. We pick these constant size steps, and we can use that in order to be able to boost our probability of success up to something that's reasonable and repeat it. So we need to make our choose our time steps to be log 2. So if we wanted to pick a time evolution of duration t, what we'll do is we'll consider tiling now our time steps, instead of into these tiny, tiny, tiny little steps that we were taking before, now we're going to choose all of them to ideally have duration of ln 2. Going up to the end. And then the last step, you can do something idiosyncratic. You can purposefully lower your probability down to equal 1/4 in order to boost it up in order to get it. But let's assume for the sake of simplicity that, t is equal to r ln 2. Okay, then you would repeat this a grand total of r times.
Sorry? In what units? I don't know if that's the question.
Oh, in this particular case, t is dimensionless because of the fact that my Hamiltonian over here, I said was a unitary matrix. So the natural units, though, to think about with t and h is that the units are inverse to each other. So you can pick the two units to be arbitrarily, because every time you'll get a t, there'll also be a Hamiltonian paired with it.
That t was the time step, no?
T is the time step, yes, but capital T here is the total evolution time that we want. And what I'm saying is that unlike before, now our time step is going to be huge. It's going to be time ln 2. Okay? And now we're just using this this fact that we can deal with this exponentially shrinking probability where we have p equals 1 up here, where we track it down to 1/4, which will end up happening at ln 2 t. Then we boost it up to 1, and we just repeat that process over and over again. And that's kind of like what's happening here, if that makes sense. So that is the simulation. Now, the one question is, well, okay, what's the value of k that we're going to need? It turns out that k is equal to what we want in order for this to end up yielding small error is we would like our error, which is order t to the capital K plus 1 over K plus 1 factorial. And we're going to want this multiplied by r. We'd like to have that equal to epsilon. So using Stirling's approximation, this ends up giving us t over k plus 1 to the k plus 1. Sorry, to the k plus 1. There's an e up here too. Is equal to epsilon. And then when we go through and find it, solving for k ends up equaling the Lambert W function of t over epsilon, which is in order log t over epsilon divided by log t over epsilon. Okay, so just trust me on this. Mathematica or Wolfram Alpha can go through and solve this, and you'll get a product log, otherwise known as a Lambert W function, when you end up doing it. And then you can go on Wikipedia to look up the asymptotics of that function, which will give you the log over log. So this will tell you how many different times we need to apply the unitary. So in our context, then what's the cost? The total number of times that that we need to apply the unitary is select needs k, which is in order of log t over epsilon divided by log t over epsilon, applications of our unitary u. And so
I have a doubt, like when we apply the amplitude amplification, that's are we applying that only on the ancilla qubit or on the whole
Yeah, actually, that's the interesting thing about this. Normally, amplitude amplification is applied on the whole thing. In this context, we're actually only applying it on the ancilla qubits. And normally that won't work. But in the case where the post-selected upon success, the outcome that you're trying to amplify is it yields a unitary transformation, you can show that actually it's possible to do amplitude amplification in this fashion. And that's where the oblivious part of oblivious amplitude amplification comes in.
But the ancilla qubit and the others, the size state isn't like they are entangled, right? So
Yes, they are.
if you apply the amplitude amplification only on the ancilla qubit, doesn't that change the state of like the complete state?
Yeah, it does, because we want, and it turns out though it does it though in a way that we want, because we want to rotate the complete state up to the state that we would have gotten if we'd gotten a success. So we actually want to leverage that entanglement in order to be able to do it. And it turns out you can go through the exact same analysis that we went through here in the event that you end up getting a unitary transformation coming out upon success. and see that, yeah, actually it ends up working, and this entanglement actually ends up carrying around the state that we want for the ride.
So the state of this, like the state psi, does not change when there's amplitude amplification happening
The
on the
state,
ancilla.
yeah, the state side does. What will happen is, because of the entanglement between it, right? What we're gonna have it rotated up to the good state, and the amplitude of the bad state is going to be diminished. So psi doesn't somehow become a tensor product between it. We end up using this technique to kill off this branch of the rotation, and that leads us only to the state psi good that we want. Even though in this context we're only reflecting the ancilla, but because the ancillas are entangled with psi good, it turns out to be equivalent.
And like the Hamiltonian we are trying to simulate, it's non-unitary, right? Not the Hamiltonian, but the unitary matrix that we are trying to simulate. So
in this case, the Hamiltonian, I assume for simplicity, is unitary. If it's not unitary, then our linear combination would need to just get a little bit more complicated, because what we would need to do if it was a sum of unitaries is now I'd have to break up this sum into further sum over j alpha j uj. And so everything goes through in exactly the same way, but in the interests of time, I wanted to focus on a case that I knew I could show entirely, rather than this case over here. But it goes through in exactly the same way, because it's also a linear combination of unitaries when you replace H with a sum of unitaries. But here,
like in the end, we'll have to measure here, right? Like
I'm sorry?
In the end, we'll have to measure here.
Well, actually, in this case, we're not measuring at all, no matter what. What we're doing is we want the whole ancilla register that determines which value of J is coming in here, and also which value of K we're getting for a particular term. We want all of that to be 0 in the end. And we're using amplitude amplification to make the probability of that measurement 100%. Okay? So in any case, let me just get back to finishing up the key point with this. So select needs a number of unitaries in it that ends up going like K. And so this implies that the number of U's needed in the simulation goes like T K, which is equal to order T log T, or sorry, not little t, capital T. That's not readable. T log T over epsilon divided by log T over epsilon. Which, if we recall, the complexity of simulation is in these units, T plus log 1 over epsilon. So this algorithm actually is individually optimal in terms of the two. Actually, technically speaking, I was a little bit lazy. The tightest lower bound is the log 1 over epsilon. So in terms of the the scaling with T and the scaling with epsilon, it's actually optimal or nearly optimal in both of those individually. So this shows you how you can actually get really darn close using post-Trotter simulation methods to the lower limit and allow you to end up getting a Hamiltonian simulation, which is linear in T. So I'm almost out of time, but I want to leave you with some of the big questions that end up existing in simulation. To me, the one that haunts me the most in this space is the question of whether or not it's true that quantum computers, in fact, can simulate the universe in polynomial time. Not every physical theory that we know of actually can be mapped into this Hamiltonian simulation framework. Much of physics can be, but not all of quantum field theory can be. And in particular, the standard model isn't known to be easily reducible to this form. And so at present, we actually don't know whether all of high energy theory can actually be simulated in polynomial time on a quantum computer. And that raises two questions. First, potentially, it could happen that quantum field theory is actually more powerful than quantum computing, which would suggest that maybe we should be thinking about quantum field computers if that's true. The other possibility, which is even more evocative, I think, is that it might suggest that actually we're potentially not thinking about quantum field theory in the clearest possible ways, because if we don't know how to compile our theories down into something that a computer can execute, then I'm not sure we really, can put it on the same level of theory that, Newtonian dynamics say is, as an example. Understanding, of course, that's one aspect to it. But on a more practical level, getting the costs for quantum simulations down to good levels. As I mentioned, the initial work for simulating molecules ended up giving gate counts that were on order of 10 to the 14. And over the last 7 years since the first gate counts were done, we've dropped this by about 5 orders of magnitude down to 10 to the 9. But the question is, how low can we go? And nobody really knows. Furthermore, nobody really has a good understanding yet of how much of an advantage quantum can end up providing for systems that may not actually be the Schrodinger equation. So if you want to look at differential equations, and in particular nonlinear differential equations, which is a natural generalization of this stuff over here, we still don't necessarily know when quantum computers can end up providing an exponential advantage for those problems. And understanding that really will help us get a grasp on when quantum computation ends up getting advantage, and also what the computational power of physical theories that might include some slight nonlinearities are. And so these questions are, of course, big ones. But, to me, I think one of the things that also is really exciting about quantum simulation is it touches on so many fields. It touches on computer science, mathematics, chemistry, physics, and it's a wonderful opportunity to end up bringing a whole bunch of diverse people together to think about these problems. And it's my hope that by bringing all of these different voices to the table, that will not only be able to come up with quantum algorithms that are substantially more efficient than we presently have, but also potentially provide an answer to this question that's been dogging me for ages about whether or not it's fair to think about us living inside a simulation in a giant quantum computer. Thank you very much.